Hello, I'm William John Holden. Let's take a look at a way that we can attack unauthenticated hot standby routing protocol. As you probably know, HSRP is a first hop redundancy protocol that abstracts the default gateway across more than one router such that networks can achieve very high availability if the active router fails. It does so by manipulating which router the active router responds to that MAC address of the virtual router. So let's take a quick look at this topology that I've built to demonstrate first. So R1, R2, R3. The cloud 1 in this diagram represents my laptop. This is actually connected to an interface. Oh, I didn't realize it was both. But that Ethernet interface isn't actually Ethernet. It's a Microsoft loopback interface. I have some static routes in my Windows routing table that point to 192.168.102.102 and 203.0.1.3.1.1.3 via the HSRP virtual IP. The HSRP virtual IP between R1 and R2 is 198.51.100.254. In every other case, the IPs in R1 is 1, R2 is 2, R3 is 3. Okay, let's just take a quick look. So we're running OSPF on this interface. We are adjacent to R2 twice on both of those switched networks and R3 once. I have a static route on R1 and R2 to get their traffic back to my laptop. I redistribute that route via OSPF using the default information originate command. The standby, you'll see that R1 is the active router. It has a higher priority than R2. Preemption is not enabled. The standby group is numbered 198. The virtual IP is 198.51.100.254. Pretty standard stuff. Standby IP, standby priority. Notice again, preemption is not configured. Okay, I could go through the rest, but I think you'll get it. Okay, so HSRP. This is an informational RFC where Cisco socializes their documentation. If we scroll down, we see the format for the hello message. Most of this is pretty self-explanatory. The version, interestingly, is always 0 for HSRP version 1, and it's 1 for HSRP version 2. Anyways, the thing I want to draw your attention to is the opcode and state. Opcode, most HSRP messages that you'll ever see are hello messages. Let's use Wireshark to see that. I'll just fire up some Wireshark with filtering for HSRP. We see some hellos coming from .1 and .2. Indeed, these are mostly hellos, probably coming every 3 seconds or so, right? It looks like it's actually faster than that, but I think it just looks that way. So diving in, version is 0, opcode is 0, 0 opcode means hello. In this case, I've chosen the standby router, which has a state of 8. The active router has a state of 16. Here's where we are told our hello time, our hold time, priority group, all that good stuff, and most importantly, of course, the virtual IP. Fun fact, the authentication data, if you don't configure it, it is the word Cisco, that 636973. That is the letters CISCO in ASCII codes. Anyways, so here we're seeing lots of good stuff. We're seeing the hellos. Everything's working normally. Again, let's take a look. So I wrote a program here, and before I do, let's just again verify that routes work. So 203. I can't remember what that IP was. I just want to make sure that I can ping that loop back over there. 203.0.1.3.1. And I can. It's working fine. If we trace route to it, no surprises, This is a little bit of a surprise. Notice that we didn't get the virtual IP as the egress interface out of R1 when the TTL expired from our ICMP traceroute. The source interface for that packet was actually .1, the physical interface, not that of the virtual IP. Kind of interesting. Anyways, there you have that. So I said that I had a loopback on this computer, so get net adapter. Look at that. There's one named Ethernet, and it says that its type is type loopback. Get net IP address for interface alias Ethernet. Okay, we have an IP of .100. And let's take a look at our routing table. Again, this is all possible because I've got these static routes that I've inserted using the route command. Okay, now that's out of the way. I have a jar here. So I wrote this program in Java, and it's kind of is, oh look, okay, so what you're seeing in the command prompt, I'm actually receiving all that traffic. I'm receiving the HSRP messages in addition to what I'm getting on there. I can show you this by join. I have using my program. I've joined 224002. If I close this program, that will go away. Notice, oh, come on. Okay, I do know that there's a bug in my program. Oh, shoot. Oh, well, anyways, boring. So I got this program, and it's sending HSRP. Oh, it's not doing anything right now. It's receiving HSRP messages on that reserved multicast group 224002. So if I want to send something out, I can do so. 254 group, I think the group number was 198. And here we've got some choices. So let me go back to the RFC and talk about the opcodes. Remember, so we looked at Wireshark, we saw that most of the messages are hello messages. Well, what's the coup? Well, the coup message, as the RFC you can see, this is when the router is configured with preempt and it wants to overthrow the current active router. So let's take a look. I don't think I even need to debug. Let's just send it. Okay. So here we saw something happened. And notice what happened. We went from active to speak state. So right now this router's in a standby state, but it changed its mind, as you can see. It went back to active. Why is that? Well, I sent one packet. This program sent one packet that with a preempt saying, you know, hey, look at me. I'm trying to preempt you. My priority is higher than yours. You know, give way. So I wonder what happens if we have a lower priority. Unsurprisingly, nothing happens. Let's show that a little better. When we turn on the debugging, we see that it received a coup message, but we also see that it's pretty well ignoring it. Okay, so let's bring that back up to a large number. Now when we send a coup with a larger, just quickly turn that off so we can read it. Okay, so this time I sent a coup with a high priority. The router correctly responds that it received a coup message from a router with a higher priority, and it switches to from active to speak. And then, of course, I wait long enough that it goes back. So that's one way. I want to now demonstrate that this is bad. I guess I can do it on R3. So what I want to show, I'm going to send some pings, and I want to show that if I send this, this is going to interrupt traffic. it's going to immediately interrupt traffic. Right, so preempt and that's super disappointing. Did it not work? All right, well, I'll go ahead and show off my other feature then. To send continuous hellos. Traffic's still getting back. Okay, finally. So I'm very surprised that this took so long. I don't know why it took so long to start working, but we see right now what I'm doing is I'm sending continuous hellos, and these hellos are actually incorrect. Incorrect in the sense that if we go to Wireshark, I'll just pause it so we can see. What am I doing? I'm sending a hello message from my computer. We see that .100 is the source. I'm sending a hello message with a high priority, telling everybody that I'm the active router. So, neat, right? So I've sent a coup. Everybody just accepted the coup that, hey, you're the active router now. And I start sending hellos, reminding everybody that I'm still there, I'm the active router. And those other routers stop forwarding. Notice that I stopped doing that, and now the pings are going through. The pings were always able to come to the PC. The problem was the return traffic. The PC no longer had a way. It no longer had the MAC address that the PC was using to try to get out through either R1 or R2. Neither of those two routers were listening on that MAC address any longer. So, bleh. Okay. So let's investigate now the second way that I've found to attack HSRP, and that's by going after the state. So the specification here has a pretty elaborate table right here that describes how HSRP is a finite state machine, and the state transitions are very clearly defined. But what happens if some rogue person like me sends it something it's not expecting? So right now, I'm not sending any hellos at all. And if I were going to send a hello, it would not be in a state active. That would be wrong. That would not be the correct progression that you'll learn about, the correct progression for HSRP that you'll learn about, I'm sorry, right here, initial, learn, listen, speak. If you're going to win, then go active, right? There's never a condition in the RFC where you just go straight to active. So let's do that anyways. We're receiving hellos. All right, again, no preemption message, no coup has been sent. We're just going to blast some hellos. And what happens? Well, the active router goes from active to speak state. It correctly realizes that something is wrong, and specifically it sends this resign packet where it says, I guess it makes it known that I was the active router, but not anymore. So, and again, we expect that, and I don't know why this is taking so long. It didn't do this when I used physical equipment earlier today, but there it goes. After a little bit, MAC address tables expire and whatnot, ARP caches expire, and now you start having a problem. So, two ways to attack HSRP. So, lesson learned: turn on the authentication. Another note about authentication: if you use plain text, it's just plain text letters, so it would be pretty easy to use Wireshark or whatever to pluck the plain text code out of here and reuse it. But if you turn on MD5, it's cryptographically secure and not known to be vulnerable to stuff. So I hope this was interesting, and I'd like to thank you for viewing.